Okay, so good afternoon, everyone, and a warm welcome to our tutorial on data-centric AI for reliable and responsible AI, from theory to practice. I'm Mihaela van der Schaar, and I'm a professor at University of Cambridge, and I'm delighted to give this tutorial together with Nabeel Seedat, my brilliant PhD student from University of Cambridge, and my brilliant collaborator, Isabelle Guyon, who is a professor at Paris-Saclay and also a director of research at Google Research and associated with Learn. If you want to have access to all the slides that we are going to present in this tutorial, please take a photo of this QR code. There are also quite a few resources there that you can download. And while you do that, let me say that we decided to dedicate this tutorial to Ada Lovelace, whose birthday was yesterday, if you didn't know, as well as to all the women in AI and machine learning. So this is our dedication to everyone. You will see also this QR code at the very end of our presentation, so if you didn't take a photo, you can do it at the time. You probably have heard this for quite a lot of time, that data is the new oil. But maybe what you did not hear so often is that, like the oil, data has many impurities. What do I mean here? Real-world data has numerous errors. Has errors not only in labels, but also in the various features that are collected. You see here an example from medicine, an area that I work a lot on, where even simple errors are often propagated through electronic health records. But this is not the only type of error. Errors abound, and because of that, they are creating AI that is erroneous as well. You see here another example, and this example is from the World Economic Forum. And I really like this slide because it's showing the issue associated with real-world data which has biases. Because of the discriminatory data that we have, the design of AI methods on the basis of this data is biased as well. And this leads to application of AI in practice, which leads to injustices. And this leads to patterns of inequality and discrimination, which create new data, which feeds new discriminatory patterns, and so on, into a spiral of discrimination. Also, real-world data has missingness. In the machine learning community, we often hear about missing labels. But this is not the only issue. We also have often missing data. And what's interesting is that this missing data may not be always missing at random. In reality, we may have informative missing data. Data that is missing for certain, for instance, individuals or instances. And this may lead at times to biases, at other times the reason for this missingness may be informative and is justified. And again, we need to learn to deal with such missingness in a smart way, because otherwise this may lead to wrong learning from data and potential inequalities. Real-world data has also numerous shifts and drifts. For instance, in the era of COVID, the pandemic changed the data we were collecting in numerous domains, and that changed over time. Also, we may have different types of shifts across different locations. So what we see is actually that data has all sorts of impurities, and unfortunately, most of machine learning is done on sanitized data rather than real-world data. And this leads often to serious issues. In this paper that I really like a lot from Sambasivan, which is entitled Data Cascades in High-Stakes AI, the issue is highlighted beautifully with this cascade. And what they show is that the data quality carries an elevated significance in high-stake AI. And in reality, these data cascades, which are shown in here, which are compounding events causing negative downstream effects from data issues, are propagated. So if we collect and deal wrongly with data, this will lead to models that are selected for no good reasons, model training that is biased, model evaluation, and finally, model deployment. So what they show also is data is the most undervalued and deglamorized aspect of AI, and data cascades are pervasive with 92% prevalence in the different domains that they have looked at, and it is yet invisible, delayed, but often avoidable. Also, most machine learning, I would dare say, often fails when taken to complicated, complex, messy, real-world scenarios. And the reason behind that is twofold. Either we have a scenario like the one shown on the left, and I just pick one of the numerous scenarios, where a very powerful machine learning model was trained on a data in the lab, and this data was sanitized and only considering the specific characteristics of that particular lab environment. But then when it was taken to the real world, the model failed. Conversely, if we train algorithms on tainted data, they learn the wrong lessons, and again, when applied in real-world scenarios, they are propagating these wrong lessons. These are two of the examples. So hence, we believe that machine learning models should be trained and tested considering this messy real-world data, and this is the data that will be seen by machine learning at deployment time as well. So with this in mind, we believe that a fundamentally new paradigm is needed for AI to orient it towards addressing such complexities of the real world. And we wrote a manifesto paper to highlight that, and we call this Reality-Centric AI. You can scan this code if you want to read more about the paper, but in this paper we outline some of the challenges, some of the issues, and also a research agenda, not solutions, but rather a research agenda that needs to unfold if it is to really build powerful AI that works in real-world domains. Pillar number 2 of this reality-centric AI agenda focuses exactly on the topic of our tutorial, that models must be designed to operate with real-world data. And here are numerous domains where we would like AI to make much bigger impact than it does today. Yet, these models need to operate in the complexity of these environments and with the complexity of this data. What do I mean by that? Data that may be diverse, may be messy, may be unfair, noisy, erroneous, missing, limited. There may be environments where we have limited or even no data. Data may be evolving or costly. So this represents really the data-centric AI paradigm that we are going to talk about today. And we believe that reality-centric AI and data-centric AI require a new way of thinking for us, the machine learning researchers, in order to engage with it and build robust models. So in this tutorial, we want to excite you, the machine learning community, to think about data-centric AI to build reliable and responsible AI. And for that, I'm going to bring an analogy to the aviation industry, where in order to build safe airplanes, every component, subcomponent, and then the final product is rigorously thought about and tested under numerous stress test scenarios. We will argue that we need to do something similar in machine learning. We need to test a lot better our machine learning models in order to be self-reliant and also to be robust and fair. We put an entire framework that we are calling data-centric DC check, which Nabeel will talk more about. But the reason I bring this here is because it represents a good layout for our tutorial. When we talk about data-centric AI, we do not only aim to talk about the input to the machine learning model. but the entire ecosystem. So we believe that data-centric AI will affect the way in which we deal with data, the way in which we train machine learning models, test them, and importantly, deploy them. With this, I'm going to give the floor to Nabeel.
Thanks so much, Mihaela, and good afternoon, everyone. My name is Nabeel Seedat. I'm a third-year PhD student at the University of Cambridge, and I'm really delighted to be giving the second part of this tutorial on data-centric AI. So as Mihaela just talked about, challenges in real data are often quite abundant, but the big issue is that they're really impactful for actual machine learning systems. So that means that data-centric AI, of course, is a major opportunity for us as the machine learning community. Not only the fact that bad data is going to affect machine learning tools that are built on said data, but when we think of putting machine learning into the real world, as shown by Gartner, around 85% of industrial AI and machine learning systems are likely to deliver erroneous outcomes, especially due to biases in data. And even from going beyond the deployment and research aspects to it, we see that this has huge financial implications when we think of taking machine learning systems into the real world. So this is clearly a huge opportunity for us as the community to really expand this research agenda a lot more, and we're hoping to get you very excited by this in this tutorial. So to really anchor things, really contrasting this idea of data-centric AI versus the whole model-centric AI paradigm that we find broadly in machine learning. So what do I mean when I talk about model-centric AI? And this current approach to model-centric AI is that when we think of data itself, it's often considered very much so a fixed asset, where we basically pull a CSV down, whether it be from Kaggle, UCI. In a company, you might query a SQL database. In the image land, you might pull a large-scale image repository like ImageNet, or you might have text repositories, Common Crawl, all of these types of data sets that we might get. And the issue is that all of these data are really considered fixed. Once we got our data set, now we can do the real machine learning. And that's where model iteration is very much the focus in the model-centric lens of how do we build new models, architectures, loss functions, and optimizers. And of course, this is a fundamental machine learning problem, and we don't say that this is something the research community shouldn't focus on. There's huge amounts of work that should be done there. But from a data-centric perspective, what we aim to advocate for is that a similar degree of focus that we're placing on the model iteration should really be placed on actual data and not just considering it as a once-off fixed step in time. And therefore, this brings up this idea of data-centric AI, where we really want to put data at center stage and give data iteration much more of a focus. And for this here, we need to build machine learning tools for data acquisition, cleaning, auditing, generation of data, and then we still have huge amounts of great work from the model-centric aspect of this broader machine learning community that we can now apply this data on top of. So that really gives you a contrast of the two lenses which we can start looking at things through. And this idea of data iteration, what we think is that actually right now, people do this task, but it's largely quite manual. And what do we mean by this? Of course, real data is not fixed, and it's very messy, being this major roadblock. But the major thing is many data scientists and engineers do all of these tasks that we listed on the previous slide, but actually do so in a very manual manner. And what this means is it requires a lot of human effort, but also a lot of human judgment, which might vary from person to person. And that's where we believe algorithms play some degree of a role here. Where 80% of a machine learning project right now is spent on data-related activities, how can we help human beings to speed this up and make this process much more easier for a human being? And especially this is important as we scale up data sets to millions of data points, where logistically it's simply unfeasible to audit millions and millions of data points. How can we help the human being really to hone in on areas of the data set which actually do require human expertise? So to really anchor things for this tutorial, just to give some sort of a definition of what is data-centric AI, and it really encompasses methods and tools to systematically characterize, evaluate, and generate the underlying data used to train and evaluate machine learning models. So we'll be talking about many of these aspects throughout this tutorial. So there's actually two parts when we think of how do we use data-centric AI. And I'll be using the term, how do we use a data-centric insight? So this is something that we can garner from the data itself. And the first is we might do something like data curation, which is the most obvious. And this is data curation to make our models perform better. And this could be in terms of predictive performance. This could be reliability, or this could be in terms of actually models performing quite fairly in the real world, so some degree of model performance. We also might want to curate data sets for the purposes of faster computation. As we have large data sets, we actually want to be much more efficient in our usage of our data. And the second is, of course, we could guide model improvement itself within the training procedure, so use our insights about the data to actually guide model improvement. And for this year, for example, you could do things like curriculum learning, where insights about the data could be used to guide a model training curriculum. In this tutorial, we'll mainly focus on the first bit, but we do have resources definitely for the second. So to really give people an intuition of what are some common data-centric tasks, and really what are some tools already out there from this broader community that we have in the data-centric AI. So the first is this idea of data characterization. How can we actually detect erroneous or noisy examples in a large-scale data set? We might do something like outlier detection. How do we identify incongruous examples? For example, you can see packages like PyOD, OpenOOD, etc. We might do missing data imputation, as Mihaela mentioned, of completing an actual data set when we have missingness, which might be at random, might not be at random. And there's packages such as hyperimpute or autoimpute. We might want to do synthetic data generation or data augmentation, where we have small-scale data sets and we actually want to augment a data set. Or we might want to share data sets from a privacy perspective. And for this year, we highlight from the community packages like SynCity, Synthetic Data Vault, YData as just some examples. Active learning in terms of actually identifying which are informative data points to label from a larger pool of unlabeled data. For example, active learning as a service, ModAL or ALIPy being examples. But what we see is that there's very many tasks which come out of all of these. And as a research community, all of these different aspects have really developed in a silo of one another and have been separate research threads in and of themselves. And what we want to put forward in this tutorial to the broader community is that actually how do these aspects actually interplay with each other when thinking that real machine learning actually focuses on a pipeline level? How do all these components actually interact with each other at a pipeline level? And actually, how can data-centric thinking help us along this pipeline to actually say, how does outlier detection interplay with things like missing data imputation? And as a community, how can we start bringing all of these areas much more together such that we can actually see this interplay that would take place in the real world? So that brings me to this area of data-centric AI for the machine learning pipeline. So up to this point in this tutorial, we've shown you data-centric AI is something really important, and as a community, we should really start paying attention, but it's really something hard to engage with. And why is this? The first is we don't really have very standardized processes of really engaging with data-centric AI. We don't have guides for necessary considerations, like what are data-centric considerations that I should be having? And we don't really have suggested tooling of what exists in the vast community that we have, but also what research opportunities are there that people should be tackling to really advance this agenda. So we take inspiration from great works such as model cards for model reporting or data sheets for data sets, and we bring out this idea called DC Check. And what this really is a data-centric AI checklist for the machine learning pipeline. And what this checklist style framework does, it aims to be for practitioners and researchers to elicit data-centric considerations from them at various stages of the pipeline, from data to training to deployment to testing. And not only providing solutions, so what tools exist from people in the community, but also showing what research openings and directions there are. And we'd love for the community to engage with this type of resource, as it's probably one of these types of resources that could, as the community expands and we start developing new things, evolve over time. So I really want to give you this idea and delve into just to give a high level of what these considerations are at all stages of the pipeline, just to give a little bit of a flavor, but we encourage you to take a look at the work online for more details. So the first is this data stage. What we really hope is that the community itself really starts thinking more deeply of how do we be more proactive from a data selection and curation perspective? How can we think much more deeply about what processing, what cleaning we actually do to our data sets at the very first place, and how that's going to affect any downstream machine learning model that we build on top of it, and how can we make this a bit more systematic and actually outline what we've actually done and what potential implications there might be. How do we actually have tooling to do quality evaluation of data sets, both for issues at sample level, but also more systematic issues of biases, and how can synthetic data itself provide realms of improvement to data sets? At the training stage, this might seem some degree counterintuitive. We're talking about data, but we're now suddenly talking about model training. So we really feel that actually data plays a significant role in how we could be guiding our model training. If we really understand our data quite well, this can really start informing how we do model design in terms of adapting our models on the basis of the data, but also opportunities to inject inductive biases into our models on the very basis of the data. If we know models are going to be used, for example, across domains, this can guide us in how we select our model training, for example, domain adaptation and transfer learning. And if we know in very high-stakes settings, for example, that we care about subgroups, we care about different groups in our dataset, this can definitely inform us to account for these subgroups and actually perform methods like group distribution robust optimization on the basis of those subgroups. But it's really by fundamentally understanding our data itself that we can apply these model training techniques. And if we know, for example, our data is going to be noisy, we can train very robustly to noise in the data. From a testing perspective, what we really think is we want to go beyond this average type of evaluation where we compute one metric on the basis of a larger, broader test set, and we hope that the community really starts adopting more of these stress tests, for example, model behavioral testing, widely used in the NLP community, synthetic data for stress testing, and also how can we do more robust subgroup evaluation to really understand where models are failing and where models work well. And then finally, from a deployment perspective, this is really the case of distribution shift on one hand, is that models, of course, data is of course going to change over time, how are models responding, but also how are we detecting these changes in the first place. We highlight some solutions, especially from the community on this aspect, but what we really highlight in this tutorial is this area around trustworthiness, is that really understanding uncertainties is probably one big thing from a data perspective, as well as issues such as out of distribution and biases and fairness in data sets itself. And this is a very important thing to account for, both from a point of selective classification when we think of deploying a model, but also how do we actually bake our training sets quite well, such that we can actually know we're reliable at deployment time. So this just really gives you a little bit of a flavor of what's contained in something like DC Check. We hope that the community really engages with this in a similar way. Model cards and data sheets have really got this engagement, and we hope that similarly we can get engagement from the community to really push this a lot further. So as Mihaela mentioned, this is also a bit of a roadmap for the tutorial. So I'll start with this idea of, at the data side, this of proactive data selection and curation and data quality evaluation. And then showing additionally how we can use this idea of data quality evaluation to also guide model training and what is out there from the community. So starting with this idea of data characterization and methods to actually curate and audit data sets. So what is the problem that we're really solving? So we all know that auditing and curating data sets at scale is just simply really, really hard. It's really time consuming for human beings, and as I've talked a bit about it earlier, when we just have millions and millions of data points, as the machine learning community starts scaling data sets, this is just simply unfeasible for human auditing. And that's where this idea of data characterization really tries to solve this problem and hone in to areas of the data set that we actually might want to audit. And to give a high-level idea, it's really this idea that not all data is equal to each other, and more specifically at a sample level, not all samples are equal to one another. And to use very, very high-level mathematical notation, this idea of data characterization is, given a set of samples, we have some sort of scoring function S that's going to assign scores to individual samples in a data set, and the hope is to do this in a modality-agnostic manner. And the goal of this really is to identify, A, which samples are learnable and important from a data set, but conversely to this, from a data auditing perspective, we really want to understand which samples are ambiguous for our models, which samples are hard for models to learn, and which samples are actually mislabeled in a data set, such that we can remove them or correct them if we have the ability to do so. We do want to highlight this idea of data characterization is very orthogonal to areas such as data valuation. And you can see a great benchmarking paper from this year's NeurIPS, which covers many state-of-the-art methods in this area, where data valuation really looks with respect to some held-out data set. Can we actually compute the value of individual samples within our training set, where data characterization really focuses on learnability of samples, and conversely, if samples are unable to be learned and what we can get from that. So to give you an idea of different paradigms, so we basically have a very noisy data set, to give you an example. So we start with what might we do in the model-centric paradigm. So in that case, we'd actually want to build a robust model. For example, we're going across a distribution, we might do domain adaptation. If we have noisy data, we might use noise-robust losses, or we might use robust layers. For example, we might use losses from other networks. We might modify the loss itself directly, we might do importance reweighting. So this is from the model-centric perspective. So let's take a look at what does this exact paradigm look like in data-centric land. So from a data-centric perspective, the goal is how can we have robust data itself and actually improve the data set, where we first want to find issues in the data, and then we want to learn without these issues and provide a cleaned up data set for model training. And for this here, to do this identification, we need machine learning methods to do so. So there's actually a wide variety of methods for data characterization from the community, which you can see on the slide here. And this is actually just a small subset, actually, that we just wanted to highlight. The first thing that we really want to show is that there's very different lenses being taken across the community to really solve this very same fundamental problem of characterizing data. Some approaches are looking at margins of classifiers, some approaches are looking from the uncertainty estimation perspective, some are looking directly from learning based on gradients and losses, and some are tracking forgetting of different samples. So there's many methods really trying to capture this very same essence of the problem. The first research opportunity that we really wanted to highlight when you look at these different methods is firstly around modality. We see that many of these methods are really focused primarily on the image domain, with a few others looking at text and tabular data sets. So there's clearly a big opportunity for the community to really start saying, what do these types of methods like data characterization look like for other modalities beyond images? And is there actually a fundamental difference? And we at least postulate that fundamentally, each modality does have its nuances, and actually building characterization methods to take into account nuances of different modalities is a very interesting research direction. The second is around tasks itself of the actual data sets. And we see most of the methods, if not all, have actually really focused on classification types of data sets. So always when you have discrete outputs. So really there's clearly an opportunity when the task itself is very, very different. How do we do data characterization? Let it be in the regression in the continuous domain, or for instance, if you are in RL domains, or if you are in, for example, unlabeled data, what does characterization actually look like in terms of selecting data points that you should be learning on? So what really brings all these methods really together is this common notion of training dynamics. So what do I mean by training dynamics, and what is this fundamental thing that's really harmonizing all of these methods that you see from across the community quite widely? So this idea of training dynamics is really how do we study the behavior of individual samples? And this idea of training dynamics actually originated from the learning theory community, where people have been studying how do neural networks fundamentally learn. And people have shown in many papers that neural networks learn samples at different rates through the training procedure. Some samples are learned early in training, some samples are learned much later in training, and some samples actually sometimes even get forgotten through the training procedure. And what these data characterization tools actually have taken as a basis of this is, if models are learning samples quite differently, is that not indicative of the fundamental underlying properties of the data itself? Where some samples, which are obviously a bit easier, will be the samples which are learned early in the training procedure. Some samples which are more challenging for a model will take a bit longer. And if a sample actually just has something fundamentally wrong, for example, mislabeled, the model might not even actually memorize it in the first place. So it's really been this idea of how can we borrow our good ideas from across different sects of the machine learning community and actually think from a data perspective, what is this actually doing? So to give you an intuition of a training dynamic, you can see it on the screen there. So this is an example of a training trajectory for individual samples through a training procedure. We see that easy examples are examples which are learned quite quickly by the model in the first couple of epochs, and the model continuously gets them quite right. We see hard examples in red trajectory. So these are examples which are actually mislabeled in an actual data set, and the model actually has no ability to even memorize these exact examples and just continuously gets them wrong through training. And then we've got these ambiguous samples, which are basically examples which the model oscillates around quite a bit because it's quite confusing for a machine learning model. And that's the real basis of data characterization, where all of them have the scoring function S, which I'll be showing across all the slides. So to give you a few representative examples, this is just going to be quite a quick whirlwind tour through many of these methods, just to give you an intuition of what all of them are doing and also how some of them are all different from one another. So the first is identifying mislabeled data using area under the margin, and their scoring function really takes this training dynamics trajectory and computes the area between the margin of the assigned logit and the largest other logit. And their hypothesis is that examples with low margin scores are actually examples which are mislabeled. So as you can see on the slide there, the image of the dog on the left bit of the slide is actually correctly labeled and has this quite wide margin, and the mislabeled example of the bird as the dog has this very low margin score between the dog logit and its assigned other logit. And they show this as a way to identify mislabeled samples in automated manner. Then deep learning on a data type, finding important examples early in training, proposed two scores in their paper, so a grand score and an EL2N score, so the first being the norm of the gradient and the other the norm of the error vector. And their hypothesis is that these very high scoring samples from the scores that they compute actually can be pruned and are very much down to noisy labels within your computer vision dataset. And then data IQ, characterizing heterogeneous subgroups in tabular data. And despite the misnomer in the name of tabular data, it also does NLP and computer vision, and really takes an angle of looking two-dimensionally from an uncertainty estimation perspective. So you first got your training trajectory where you have a confidence score and computing an average confidence, and then actually computing fundamentally an average aleatoric uncertainty via doing decomposition of the variance from the law of total variance. And what that really reflects is the variability due to our inherent inability to predict with certainty. So this is the actual uncertainty in the data itself. And the hypothesis from this paper is that ambiguous samples, which can now be characterized because of this two-dimensional nature, are actually these very uncertain samples that oscillate around a lot. And the hard examples are those which just have low confidence despite the fact that we have low data uncertainty. And these samples can also be pruned from a data set. Then dataset cartography from the NLP community actually is relatively similar and actually takes an approach from an epistemic perspective, so really looking at uncertainty in the model itself. So this is variability as our parameters change through the training procedure. So really looks at how is the model really detecting it. So rather than looking directly at the data, really takes a model-centric aspect to this and has a very similar hypothesis from the perspective of pruning. And then variance of the gradients from the computer vision community look at estimating example difficulty via variance in gradients. So actually looking at gradients of very challenging examples actually just oscillate quite a lot during the training procedure. And as you can see on the slide there, these examples of apples, which have very high variance of gradient scores, just look really, really different from this conventional, typical, pretty-looking red apple that you might find in CIFAR 10 as the most typical example. So actually showing us an automated way to actually detect such type of samples. Then from a loss perspective, this has actually been primarily from the noisy label community, so something called small loss. So this was often used for sample selection with this idea that very large loss samples through the training procedure are also likely mislabeled. And then finally, this example that I last show here is actually not a training dynamics-based method, but talking about data characterization methods would really be amiss without mentioning something like CleanLab. So CleanLab actually takes a different approach, not of training dynamics, and actually given a model and a noisy data set, they predict outputs from this model with a goal of really estimating finally a noise transition matrix. And they do so first by estimating something called the confidence joint, which simply can be done via counting. So you've got your noisy prediction, and you've got your potentially noisy label from your data set, and you can count the correspondence, and then they produce a normalized matrix, which you can see as an estimate of the noise transition matrix, and they use this to then audit a data set, where, for example, the off diagonals, you can see that 10% of dog images are likely to be in reality foxes, and they use this noise transition matrix to then audit data sets. And then finally, something called triage, which is going beyond the classification settings up to this point has been things which has all been classification, and really getting this idea that this is still training dynamics, but really the fundamental aspect of data characterization is how do we get a good principled scoring function. So what triage does is it actually uses something of conformal predictive distributions to produce a probability in this continuous setting and uses that to actually audit data sets with the goal being, or the hypothesis, that high or low CPD probabilities which evolve through the training procedure can also be sculpted from a data set. So this has been just a high-level whirlwind through many of the methods. They were selected not specifically. There's definitely many, many methods we could have covered in this tutorial. But at this point, now that you've seen some methods, you might say, what can I actually do with these methods? How are they super interesting for me personally? So let's look at how a data characterization method might be used to audit different data modalities from text to image to tabular data. So what would a data characterization method give you if you're auditing a text data set? For example, if auditing something like IMDb, the IMDb movie review dataset, easy examples would be examples here of movie reviews, which you can see in red. These are actually correct negative reviews, and positively, these very green ones are positive reviews, so this is correct in the dataset. What's quite interesting from the ambiguous group, this actually picks out linguistic ambiguity in text where despite the review being labeled as actually quite negative, we see that part of the text is actually quite positive, part is quite negative, and there's actually this linguistic ambiguity being surfaced by a data characterization method. And finally, from the hard perspective, these are clearly mislabeled examples where somebody who was annotating a data set would have put a positive label, but clearly the thing is very negative, or they've assigned a negative label, but the text is really, really positive in the movie review, and we can audit this with a data characterization method in a very automated manner. From auditing an image dataset, for example, easy when auditing the Celeb A dataset would be these quote-unquote very crystal clear looking images, so it's expected that the model would be good to train on. But what's interesting from a fairness perspective is the ambiguous group actually from a data characterization method showed that a machine learning model would find females with shorter hair being considered ambiguous. And clearly this is very, very problematic and something we don't want to imbue machine learning models with. And this is actually showing the value of a data characterization method to really surface these issues in data sets to human beings such that they can go away and rectify their data sets such that we don't imbue machine learning models with issues like this from our data sets. So I think highlighting it from a responsible AI perspective, why such methods are actually important for us to develop as a community. And then from the hard perspective, once again, these are incorrect ground truth labels. And then finally, from a tabular data perspective, what's actually really interesting and why we want to show it is that actually differences in modality really guide our thinking quite differently for actually doing data characterization and why it's important for the community to focus on a variety of different modalities. So to give you an example, this is a prostate cancer detection type of task where given a set of patient covariates, somebody would want to predict if a patient might have a mortality outcome or not. So easy samples would be as expected. Patients who are not very severe, they have something called a low PSA score. They have low prostate cancer stages that end up surviving. And severe patients who have these very high PSA scores actually typically have the mortality outcome. This is quite expected. What's very interesting from an ambiguous perspective is that these are actually patients with very similar features, but yet their outcome was very, very different. And why is this actually very interesting? So compared to images and text where we can't add more data, we can't add more information to an image, what we can actually do in tabular data is we can go away and collect more features. A doctor can go run more diagnostic tests. So these would be examples of samples in a data set where somebody is guided to go collect more samples or a clinician to go run more diagnostic tests, to add more information, to actually do the disambiguation. So that's something that a data characterization method would be able to offer. And finally, the hard example, this would be patients who have something called a heterogeneous outcome and we'd actually want to highlight to a clinician to really audit. So really highlighting why is this an interesting perspective of looking at different data modalities. And then finally, from the perspective of, I've shown you many aspects of how you could audit a data set, but we also think about, we actually want to take these insights and guide model training to be much more reliable. So the first is we might actually use a data characterization method to sculpt the data set for more reliable performance. So to generalize better, we remove these hard examples, we remove some of these ambiguous examples, and many papers across the literature have taken this approach. But additionally, what's actually quite interesting, this idea of doing group distribution robust optimization guided by these surface groups from a data-centric method is one interesting manner in which data-centric insights garnered at the data level can actually start guiding how we actually train our models to be much more robust. And if all of this is really, really exciting, and you've got to this point, you're like, okay, the examples are pretty interesting. How can you apply data characterization to your own data? So as part of this tutorial, we've put together an open source package called Data Agnosis that we love to share with the community. And what it really aims to do is bring all of these data-centric methods or data characterization methods from this tutorial and actually bring it and make them very easy for you to engage with. So we provide a unified interface and API in sklearn format, which makes it really easy to engage with. And we bring 12 state-of-the-art methods from across the community highlighted in this tutorial with an easily extendable plugin style as more methods from the community really start getting developed. And we hope that the community more broadly can start engaging with this and really contribute as more methods get developed and we grow this area because we really think it's an important area for the research community. So to give you an idea of how relatively easy it is to use, so you could pip install it. Of course, you need to get your data that you might want to audit. So let's say you might get the iris data set. It's probably unlikely in reality, but just for purposes of demonstration. So you then need to create something like a data handler to really pass your data in. So basically creating the PyTorch data loader object. And then, as mentioned, data characterization really is based on training dynamics. So this idea of actually, we need a model in the first place. So defining one model, let's say it's for images, you might do a computer vision model, you might use a transformer for text-based data. And then you need to get your data characterization method via a plugin. For example, let's say you want to use the variance of the gradients method, so you can simply define VOG and do the get function. And then you call fit on your data handler, and all is taken care of nicely under the hood. And you're able to get all of these scores that I've talked about in this tutorial. And then once you have the scores, the practitioner or the researcher can go away and use these scores based on the actual application. So we have more tutorials on usage, other plugins and modalities on the GitHub, and we're excited if the community to contribute to this. So just in terms of the tutorial roadmap, we've clearly covered relatively a fair bit of ground right now. I finally want to end on a little bit of enabling trustworthy predictions, so beyond supervised learning in the world of LLMs. So this is where trustworthy ML meets data-centric AI. So we know typical machine learning models really have point estimates. So we produce this point estimate, but from a decision-making perspective, when we have a point estimate, it's just really confusing to know whether we should trust this prediction or not. And the most common method from trustworthy machine learning community is imbuing uncertainty estimation on top of it. For example, putting a predictive interval over something. And this allows us to judge whether we trust the prediction or not. And the question is, there's many uncertainty quantification methods, and we really want to ask is, up to this point, we've talked about data having fundamental issues and we need to audit data sets. But can data itself help us actually improve machine learning? So to give a little bit of a case study, we want to show that can data itself provide interesting signals to help improve something like uncertainty quantification? And the key idea of this work, and it's something called self-supervised conformal prediction, is this idea is that data itself can simply be reused as additional signal to help improve models. And what do I mean by this? You might have a labeled data set and you could do self-supervised learning and pretend you've never ever seen the labels, and you get a self-supervised signal that you can provide into a predictive model. Or additionally, you have unlabeled data itself, where in many cases, that's where many uncertainty quantification methods actually struggle in areas of sparsity of our labeled data, but you might have a lot of unlabeled data in these more sparser regions, and could unlabeled data help you there? So we just wanted to highlight more broadly this idea of data being reused to provide additional signals to machine learning models to show you that it's not just only about auditing. There is actually very interesting research to be done of how we can reuse data to obtain interesting signals to help models. And then, of course, no tutorial at this very moment in time would be complete without mentioning data-centric AI and their relationship to the world of LLMs. So as we all know, training of LLMs is fundamentally really about the data itself. As shown in the paper, Textbooks Are All You Need by Gunaseka et al., who've really shown you that understanding and having high quality data when training large language models really helps you to get to levels even compared to models which use much more amounts of data. Not only that, OpenAI and open source developers, for example, like the Technology Innovation Institute that developed Falcon, have also shown that the biggest issues that they found when training large language models is errors in data during model training itself. And they've done extensive filtering of things like the pile and common crawl to really get high quality data sets before training large language models. And because it's not really all about the model, and it's really fundamentally about the data, what we want to put the challenge to the community more generally is, how can data-centric AI itself and data-centric AI methods make this much more systematic and principled and actually help the large language model community also push forward in terms of how do you audit these very large-scale data sets in a much more automated manner. So that brings me to the end of my section of this tutorial. Mihaela, I hand over to you now to talk more about synthetic data, both at the data point as well as synthetic data for testing. Thank you so much.
First, I'd like to say that we are going to take questions at the very end and before the panel, so sorry for asking you to stick with us for a little bit longer. So as Nabeel said, I'm going to talk now about synthetic data, but not about synthetic data in the way you may have heard about being talked in the past. The whole agenda of generating synthetic data to be able to share it with the community without breaching the privacy of this data is an important topic and a research area in itself. And as a matter of fact, we are having a workshop dedicated to this topic later in the week, when we are going to describe about synthetic data and its uses for sharing data, and especially privacy preservation. So please join us on Saturday if you are interested in this. And a related sister workshop is going to take place on Friday, which is a workshop on deep generative models for health. And if you are interested in learning more about synthetic data, together with two former students, I've given tutorial on synthetic data at previous conferences at ICML 2021 and AAAI of this year, and you can find them online. Today, though, I would like to take a very different spin on synthetic data. It's used to improve and deal with issues that real-world data cannot. So it's a scenario where synthetic data is not a second-rate copy, but rather an improvement on top of real data. So we are going to talk today about synthetic data powerful creation, not second-rate copy. And in particular, I'm going to talk about how synthetic data can improve issues associated with fairness of data, how we can use synthetic data for augmentation in the case our data sets are relatively small for certain subgroups. How can we use data from a source domain which has plentiful data to another domain where we have very little or no data? And finally, how are we going to use synthetic data on the basis of real data to better stress test our machine learning models, moving to next generation training, testing, and deployment? I'm not going to talk about privacy preserving synthetic data because that's a topic of its own. As I mentioned, past tutorials dealt with that, and I'm not going to talk about LLMs. Okay, so how can we use synthetic data as an essential ingredient of data-centric AI? Let us talk first about fairness. So in this paper of NeurIPS 2019 by McDuff and collaborators, simulation-based approaches has been used for interrogating classifiers using generative adversarial model in a systematic way. And what you see here is how they have generated this synthetic data to test the quality and the fairness of a variety of image classification problems, from face detection to gender classification. And what I especially like in this work is that the laws that they have used allow for exploitation of failures with respect to bias, and is combined with the diversity loss to promote exploration of the parameter space. So this is a very interesting way in which synthetic data was used to stress test the ability of machine learning classifiers to really deal with bias or not. Another thing we can do with synthetic data to go even one step further is to ensure that if we are dealing with unfair data, we can use synthetic data to improve the quality of the prediction. How is that? We know that unfair real data can lead to unfair downstream prediction, and what synthetic data can do is create fair synthetic data on the basis of unfair real data to train machine learning models such that they lead to fair prediction on real data. And this is work of a few years back that we call DCAF, which stands for Generating Fair Synthetic Data Using Causally Aware Generative Networks. Numerous notions of fairness exist, and I'm highlighting here notions related to group fairness. For instance, let us take the example here on the left where someone gets a loan, and that shouldn't depend on gender. Maybe it shouldn't depend on education, but should receive an income And hence, what we are interested here is conditional fairness, for instance, which may make the most sense. But other notions of fairness could be applied and could be of interest. So what can we do? Well, at the first glance, it may seem that we can create fair synthetic data by eliminating, for instance, the relationship between the gender, which is the protected attribute, and the other features. However, if we do that, synthetic data may seem fair, but the reality is that if we apply this and we train machine learning models on the basis of this seemingly fair synthetic data, when we are applying it to these predictive models that are trained on the basis of the seemingly fair synthetic data, to the real data, we are going to still keep a relationship between the variable B, which in this case education, and the outcome. So masking of the sensitive attributes does not remove the indirect discrimination, which then the machine learning models will learn. So we need to guarantee fairness for the downstream model. So this has not been sufficient. So by not debiasing correctly the data, synthetic data may look fair, but may lead to biased downstream models, which is an issue. At this stage, you may think, well, I should remove all the possible relationships between the data and between the different features and the outcome, but this, of course, will not lead you to anything that's useful in practice. So what we do in DCAF, we take a causal perspective to provide an intuitive way to achieve different fairness notions. And of course, this does rely on us having an underlying causal knowledge, which we can then use to guarantee fairness for the downstream task. In this way, DCAF becomes effective because it enables us to use local distribution modification to preserve the overall data quality and just remove the unnecessary links. So how do we do that? We train a generative model based on the known causal structure of the data and determine which edges lead to unacceptable bias, and we do targeted biased edge removal associated with the notion of fairness we want. So in this way, DCAF is comprised of several generators, one per variable, that learns these causal conditionals observed in the data. Then at inference time, the variables are synthesized topologically using the causal graph, starting from the root node and going all the way to the leaves. And various data sets can be created using different types of notions of fairness. And indeed, with such an approach, the quality of the data is preserved, so we can build high-quality classifiers while being compatible with different notions of fairness. But this is just the very beginning of the story. I feel that as a community, we need to go a lot further in using creatively synthetic data to improve the fairness of our real data. Are there other ways to debias data than causality? Also, what about other modalities, especially time series data? And what happens if the bias keeps evolving and keeps changing over time? And also, what if we have bias in the data and also missing data or noisy data? So the challenges are multiplied. All, let's say, open research agenda for us. Let me now take another example where synthetic data can be useful, and that is augmenting small sample data sets. You see here an example from a paper by Chen and collaborators, where a variety of medical data sets where we do not have a lot of data exist. And what they have shown is that by really synthesizing for these very small data sets in smart way additional synthetic data to augment their small data sets, they can use this combined real and synthetic data to improve the quality of their classifiers. So hence, through a process of smart augmentation of these images, improved classification is possible. While these type of examples are starting to emerge in both images as well as text, the reason behind that is the invariances are very clear in these types of modalities, images and text. And hence it is using this type of known inductive biases that we can use to augment data. This is, though, a lot more challenging in tabular data. And let's not forget the real-world data abounds with tabular data. What can we do in that case? Because it's not a question of just creating some translation or some temporal translation. We know that inductive biases in tabular data are weak, so we are left with a challenge. And one potential idea is to use the data generating process being described as the relational structure. And by learning a relational structure in this type of tabular data, we can go through a process of smart augmentation. This is what happens in Google, where tabular data is generated by learning automatically a relational structure. So unlike in decaf, in this paper, Google, the structure and the relationships between the tabular data is learned simultaneously with the generative model. And in this way, through this process of joint generation, a VIE architecture is learned that is capable to understand the inner structure of the tabular data. It is through this process then that augmentation can be done by exploiting the relationships between the data. But again, this leaves us with a lot of research challenges as a community. First, are there better ways than just learning graphs to capture the structure of data, such as tabular data? What about high-dimensional data, when the relationships may be even more complex or more complicated? And what about augmentation of multimodal data? Can we use the relationships between these different data modalities to augment data more carefully? We talked a little bit about data imputation, and I really feel that this is an overlooked area in machine learning. We are not going to talk about it today because I really feel that it deserves its own tutorial and its own attention. So we brought together some resources associated with it that we could find at this particular webpage. But the reason I'd like to bring attention to the community to data imputation is that the problems abound, and the more interesting problems are related not to data imputation where data is missing at random, but rather data may not be missing at random, it's informatively missing. And an even bigger challenge, as I alluded to, is in the case we may have biases associated with missing data, as well as data may be missing in time series settings, where the presence and absence of information may tell us something about the data. So here it's not just doing generative modeling, it is really being very careful about the patterns of missingness. Now, what happens in yet another setting? A setting where we may have a lot of data in one domain, the source domain, but very limited or possibly no data at all in a target domain of interest. Let us take two examples, but these examples are not limited to healthcare. We may have, for instance, in COVID, a lot of data initially in one particular hospital, in one particular city, which may have a certain type of distribution of patients. But then as COVID progresses, another hospital may be hit by COVID, and this hospital may be very different in terms of the data distribution. Yet, can we learn on the basis of what has happened in the first hospital for the target domain of the second hospital? And the problem is becoming even more challenging if there is a mismatch in the capabilities of these two hospitals, because we don't have then just distribution mismatch. We may also have, in addition, feature mismatch, because different features may be captured across the different domains. How to deal with this challenge? This is very much a data-centric challenge, but is one where generative models can help. So I try to make here a summary of the different works related to this question. First, what happens if the source and target task have the same feature space? If they do, a second question can be asked. Were the source and target task having the same distribution? If the answer is yes, then vanilla generative models would be useful. But if the answer is no, we need to do conditional generation. If the source and target task do not have the same feature spaces, and this is a very interesting and important and yet much less looked at area, then a question is, were the source and the target task, again, having the same modality? If the answer is yes, we deal with domain translation, and if the answer is no, we need to look at cross-model generation. And while you see a few works in all these areas, and some areas have a little bit more work than others, still this represents a very understudied area. So, can we determine better which data we'll be needing? In many of these works is the assumption that all the data from the source domain may be relevant to the target domain, but that may not be the case. How much data we need, and from which domain? If we can select from where to collect the data for the source domain, if we have this luxury, how to do that in a principled way? And can multimodal information help? Let me now move to an area that I'm extremely passionate about, and that is using synthetic data to better test our machine learning models. Again, I feel that while we can congratulate ourselves in the machine learning community for building more and more powerful machine learning methods, the reality is that in many real-world domains, machine learning is not making the impact I would like to see. And I will say that one reason behind that is that we do not test well enough our models. We often just use still the good old paradigm of having a holdout data set on the basis which we model select and determine the performance of our models. But the reality is that if our machine learning are successful, they will be taken to the road, a complex road, a road which may look very different than the lab setting in which we trained and tested these models. So like in aviation, we need a new paradigm. And what I propose as a new paradigm here is to generate realistic synthetic data for many scenarios that we do not have in our training data. Two examples, and these are just two of the many examples I can envision, is we would like to test better granular and more granularly on minority subgroups. And also we may envision a variety of distribution shifts as well as changes over time in the distributions we see. Let me just give an example here. Maybe our data set has only a limited amount of relatively elderly Black people. If it is to train and test our machine learning models and select machine learning model on the basis of this biased data, we may select a model that's not going to be adequate in the real world. Also, the data may be limited and may not have distributional shifts, which we may see when we take the model to the real world and hopefully deploy it for many years to come. So what we try to do here is a new methodology to much better test the data, and we call this Freest testing, which stands for synthetic data for subgroup and shift testing, and Boris and Nabeel will talk more about that in this NeurIPS. What we do there is we take limited real data, for instance, for small subgroups, and train a conditional generative model on the real test set, then generate synthetic data conditionally on various subgroups or shift specifications of interest, and finally evaluate the model on the generated data, which allows for a much more comprehensive evaluation than just the conventional training testing paradigm we apply today. To highlight this, you see here a variety of data sets, and many more exist in the paper, where we have different types of subgroups. And what you see is that for the smaller subgroups, if we are just testing on the holdout data set, we may end up with really a very high variance and a wrong model being selected. So what synthetic data can fix this by creating a much more diverse and representative test data. And the best results can be obtained, of course, if we combine synthetic and real data. But this is, again, I feel, just the beginning. I'd like to kind of compel the community to think much more about how can we really use available data combined with synthetic data to stress test our models. What happens if we want to have different types of shifts and drifts? Can we plan better for the future? And can we think about new paradigm of testing our models, not only predictions, but also interventions, actions, or reinforcement learning? Now, let me just say a few words about synthetic data in general and its data quality. Well, clearly we need to use synthetic data that's of high quality, and it's by now well known that just scale divergence for assessing synthetic data is not enough. We need to quantify the quality of synthetic data at the data level in a meaningful and interpretable way. And for instance, notions of fidelity, coverage, and authenticity have been brought forward to assess the quality of generated synthetic data. But this is, again, not enough, because often people create fantastic data first and then generate synthetic data that's equally fantastic but not representative of the real-world data. So statistical fidelity is not enough. Our data sets, our real-world data sets, are full of impurities, as I mentioned at the beginning of the tutorial. They have noise, they are mislabeled, they have all sorts of missingness and measurement artifacts. And if it is to use perfect synthetic data to create all these machine learning models, we didn't solve the real problem. So what we need is to create synthetic data that is equally realistic and hence deals with these impurities. So data-centric AI need to meet synthetic data to enable really high-quality testing of data using synthetic data. And for that, we created a comprehensive benchmarks that really brings together the world of synthetic data and data-centric AI. Now, this kind of brings me to the end of this part of the tutorial, and I highlighted kind of new uses of synthetic data, not only to share it instead of real data through privacy preservation, but rather using synthetic data as an improvement on top of real data to allow debiasing, augmentation, imputation, transfer to domains where we have very limited data, and enable us to do improved machine learning testing. If you are interested in all of that, we are building actually open source community, and I really want to recruit as many of you interested in these new uses of synthetic data, and all the different tools that you have seen in this part of the tutorials are part of it. And this is this open source package we call SynCity. And what's nice about it, it has different types of modality, not only imaging, but also tabular and time series data. And we hope that if you are a researcher, you are going to help us build the community further, because this enables us to do rapid prototyping as researchers, but also as practitioners, we hope that you are going to contribute to use this in the real world. This brings us to the final part of our tutorial, where Isabelle is going to talk about benchmarks and competitions. Isabelle.
So thank you for sticking to this tutorial to the end. And now we're going to shift to some kind of a hands-on tutorial. And you're welcome, if you have your laptop, to try it yourself. And so I'm going to talk about competitions and benchmarks and how to set up your own competition. So if you want to follow it as a hands-on tutorial, you can either with your phone grab this QR code, Or you can go to http://codabench.org with your laptop. And on the front page of this website, you can click on the Get Ready instructions. I'll let you do that if you want. Be careful, you have to type HTTP, not HTTPS, otherwise you won't be redirected correctly. So in the meantime, while you follow these instructions, you'll get another chance, of course, to do that once I go through the introduction. I'd like to walk you through a little bit what it is to create a challenge or a benchmark. So recently, David Donohoe wrote a very interesting paper called Data Science at the Singularity. According to him, a data science-driven phase transition crossing a kind of singularity is happening now. And not the AI singularity, the moment when AGI is achieved. This hasn't happened. Rather, some kind of, some fields in computer-driven research are approaching a reproducibility singularity. What is that? So the moment when all the ingredients of frictionless reproducibility, also called FR, of computational research are assembled in a package that makes it essentially immediate to build on the work of other researchers on an open global stage. So the emergence of frictionless similarity FR, according to David, follows from the maturation of 3 data science principles that came together after decades of work by many technologists and numerous research community: data sharing, code sharing, and competitive challenges. However, implemented in a particularly strong form of frictionless open services. So this is what I'm going to tell you about today, how to create these competitive challenges to bring up frictionless reproducibility. So in a keynote presentation that I gave last year, I already highlighted a list of hurdles that prevent us from doing reproducible science, which include private code, private data, biased data, cost of experiments, restricted access to trained models, leaderboard overfitting, and no reporting of negative results. So if done properly, competitions can help you overcome these hurdles. So after years of efforts, we've been putting together an edited book to help people conduct the design of challenges of benchmarks in a proper way. And I'll be talking to you about chapter 2 today, the challenge design roadmap. This chapter was co-authored with Hugo Heyer-Escalante, Addison Howard, Walter Reed, and Sébastien Traeger. And most of the illustrations in that talk are generated by AI. So in taking you, along this journey of organizing challenges, I will take this analogy of organizing a new trip. And first it starts with gathering your tools. In gathering your tools, you first need to find a good problem, that is, have clear scientific objectives, scientific questions, and importantly, have a problem of calibrated difficulty for your audience. And the second tool is proposal review. So fortunately here at the competition track of NeurIPS, you get a chance if you submit a proposal for a competition to have your proposal reviewed for novelty impact and protocol soundness and also pitfall avoidance. Then you need good logistics, a team, resources, good beta testing. And finally, to ensure good participation, you need to have incentives like prices and figure out how to target your audience properly, and a dissemination plan, which is very important if you are targeting the academic community, because publication is key for progressing in your career in academia. The next step is assembling your team. So complementary skills are needed, as listed here: coordination, challenge design, domain expertise, method, data quality, beta testing, fundraising, communication, analysis, and report writing. So you need a well-rounded crew with diverse skills. And next, you will need to find some mission objectives. So there are different types of challenges. There are recruiting challenges, which objective are to find champions. Then the approach to that is to select problems that are representative of real scenarios. Then the participant expectations will be to handle all aspects of the problem, including pre-processing and API design. And the deliverable is a technical report, maybe in a top tier of the top ranking participants. This is kind of different from research and development challenges, which objective is to focus on specific scientific questions or bottlenecks. And the approach maybe is to design a detailed API for the participants to work with. And the winners may be required to open source challenges. Quite similar, academic challenges where you want to be able to discover the solution to a complex problem, and the approach may be to have incremental steps and organize first hackathons or dry run to ramp up a community of experts that will solve your problems. And then you may be selecting the winners not only based on the leaderboard, but also based on paper writing and giving best paper awards. You also have public relation challenge that are more, geared towards, attracting customers or attracting students, and branding challenges that are meant, to gain visibility for companies. Then, in the process of, organizing your journey, you must know the locals. And by know the locals, I mean determine what your target audience is. So your target audience could be made of novices, professional data scientists, researchers, and academics, industry engineers, ML enthusiasts or hobbyists, students, competitive coders, innovators, or entrepreneurs. This is such a diverse type of people who may be entering your challenge that it'll be very difficult to adjust to the different levels of expertise, motivation, and time commitment to cater to all of them. So you might want to right away think about who you want to target first. And next, on your organization of your journey, you want to do a little bit of discovering the terrain. It's very difficult to get everything right the first time. So particularly if you're venturing into solving new problems that you are crowdsourcing via the organization of a challenge. So you must first experiment with the type of data, metric, baseline methods, and information available. So do you want to treat the problem in an abstract way or include domain knowledge? To get results, it's important to tune the difficulty of the challenge to the audience. So one thing that we've been doing, which is quite interesting, is organizing first inverted competitions in the process of working on the challenge organization. And what an inverted competition is for the organizers themselves to participate to a competition in which they submit data to baseline methods as opposed to submitting methods to various data sets. And in doing that, the organizers compete towards defining the tasks that are best suited to solving the problem of interest that they want to illustrate in their challenge. And what is the key to the treasure? Well, the key to the treasure is to focus the challenge on a set of main scientific questions. One of the, I would say, trap that organizers fall into often is not to have a very clear scientific question for the participants to address, or have multiple scientific questions, which confuses the participants. So scientific questions can, follow the whether, why, what, how, and what for kind of schema. Whether would address comparative questions like, The most common type of questions, in fact, for challenges are weather type of questions. So whether there is a method that significantly outperforms the baseline method, or more subtle, compare performance trade-offs. For example, in a challenge that we call agnostic learning versus prior knowledge, the question was whether prior knowledge was needed or not to do pre-processing. Then there are what competitions? So more like discovery challenges. One of them was the Higgs boson challenges, in which the problem was to discover signatures that are revealing of given particles. So what signatures in data reveal new high energy particles? There are why challenges that try to uncover causal questions. So why did sales decrease? Why did crime increase? Why did the opioid epidemic spread? Etc. There are how questions that are prescriptive. So these are typical of, for example, optimization challenges. What maximizes a given reward in various settings. And there are what for challenges. So for whom might this model be unfair or biased? For what population does this model perform suboptimally? For what new task or new domains can knowledge from one domain be useful? So those challenges are typical, for example, of fairness problems. So now you're close to the end of your organization, and you want still to chart the course of your journey. So peer review is extremely important. Here at NeurIPS, we've set up a peer-reviewed system for competition in the competition track. So I would encourage you to make use of it. It's very competitive at NeurIPS, so you might want to identify first a second-tier landing conference and run a first draft of your competition. We do that ourselves very often. There are a number of other conferences that run competition programs that are less demanding than NeurIPS, and then we the next year run here a competition at NeurIPS. Hopefully, the reviewers will be helping you identify common pitfalls. But you can do that to yourself by using this checklist. And so one of the common pitfalls is having unclear challenges that have multiple questions instead of one primary scientific question. Then another hurdle is difficulty calibration. So you must match the difficulty of your challenge to your intended audience. Challenges that don't have a high participation, usually it's because the difficulty of the challenge wasn't matched to the audience. So in order to adjust the difficulty, you need to lower the barrier of entry, and it's very important to provide a starting kit. And then, of course, to beta test absolutely everything, including, of course, the starting kit, to make sure that everything's working properly, because you might discourage your participants in the first few days of the challenge if they try to enter and things are not working. Those are busy people, like everyone, so they won't come back, if they find not everything's working right. So organizing a challenge is a little bit like, preparing for a product launch. It's very, very demanding. You need to also prepare good incentives like prices and communicate well with your intended participants. Let them know in advance that the challenge is coming up so that they will be reserving enough time in their schedule to participate, and monitor participation and keep, answering questions on the forum or stimulating participation by giving harder baselines, etc. Another very important thing is to discourage cheating one way or another, or monitor, all sorts of way in which people could be cheating. And the reason is not so much that you want to catch cheater, is that you want to reassure participants that are very serious about entering the challenge, that they will win for a good reason, that there are no participants that will by chance, and that it will be really their capabilities that are that are rewarded in the challenge. And finally, there is this problem of quantity and quality of data that, of course, is the central piece of this tutorial. The easiest thing is maybe, is there enough data? So you can test for that by looking at whether the error bars of your predictions are good enough. In terms of a challenge, actually, it's not just the error bar. What you want is to have ranking of participants that is stable. Unfortunately, at the beginning of your challenge or while you're preparing the challenge, you don't have the ranking of participants yet. So you need to kind of anticipate that, which is why it's very useful to be running hackathons or dry runs of your challenge. So actually, an interesting anecdote is that a few years ago, when I was running one of my first challenges, one of the lawyers of a company we were that was sponsoring us added to the rules is that this is a skill-based contest in which chance plays no role. And that kind of spoke to my mind. I thought, how can we make it that chance plays no role in a challenge that is based on data? So in the 1990s, I stumbled upon that problem. How much data is enough in a test set to ensure that chance plays no role or as little role as possible? Interestingly, I found at the time that there is a counterintuitive result. The smaller the error rate is in a classification problem, the larger the amount of data that you need to test. So how do you understand this intuition? Well, assume that the error rate is 1%. That means that on average, you see only one error for 100 examples. And which means that you need to have at least 100 examples in your test data to see one error. And likewise, if you have an error rate now of 0.1%, you will need to see 1,000 examples to, on average, see one error only in your when you perform testing. So if you do the math and look, at error bar, theory, you can come up with a rule of thumb, of course, under simplifying assumptions of IID data and normality. But that is easy to put in place in practice, which is NP equals 100, where N is the size of the test set and P is the anticipated error rate of the winner. And that holds also only for small error rates. But what that says is that the error rate is, the number of examples in the test data should be inversely proportional to the number of samples in your so the number of samples in your test set should be inversely proportional to the error rate. The error rate of whom? Well, the anticipated error rate of the winner. So in bonus, at the end of the slide deck, I give you an enhanced formula that is applicable for any additive loss, not just error rate. But interestingly enough, this is good, for dimensioning your test set more or less, but it's not good enough for accounting for all the possible factors of variability. Here, this is only the factor of variability which is due to drawing a certain test set of a given size. There are multiple other factors of variability usually into the design of a challenge, which include the data split between training and test, includes also eventually seeds for the models that you're testing, which may include, other things like if you have multiple tasks, there is the variability between tasks, etc. So over time, we've been creating two-phase challenges in order to overcome a little bit of that problem. One of the things that two-phase challenges address is that there is this counter-intuitive fact that when you organize a challenge, you want to have the largest possible number of participants. But the larger the number of participants, the more unstable your ranking is going to be. It's a little bit a problem that people know in statistics as a multiple testing problem. Each participant is kind of giving you one result for the solution of your problem. And if you have many participants, it's like you're trying to solve many times the same problem, and therefore your error bar gets worse, as learning theory predicts. So there's this, trade-off between having a lot of participants to declare that your challenge is successful, and not having too many participants to keep good error bars as organizers. So to mitigate that, what you can do is to have a first phase during which you eliminate a great number of participants who are not competitive enough, for example, that don't perform significantly better than the baseline method that you provided. And then you have a dedicated final phase with new data in which you only run the top ranking participants. All right, so this is only one of the difficulties, which has to do with getting enough data and ensuring that your ranking is stable. Another difficulty is the problem of bias in data and data leakage that Mihaela and Nabeel touched upon. So this problem is so much bigger and takes so much more time to address in a short tutorial that I'm pointing you here to a tutorial by Causal that addresses it a little bit more at length. But in a nutshell, you have several types of problems that can creep into your data, including sample bias. So some groups could be over or underrepresented. So you probably know the well-known problem of face classification. That's for example, if you would take examples of faces from NeurIPS, it would maybe be male-dominated, so classifying faces of black female might get much higher error rates. There are spurious dependency bias, also known, as shortcut learning. So, for example, if you would try to classify images of pets and take all the pictures of cats indoor and all the pictures of dogs outdoors, you would have a luminosity bias that makes classification very easy, but not based on the shape of the objects of interest. And then you have information bias that is maybe even more subtle. It is induced by data preparation. So an example would be to include incorrect features. For example, if you wanted to predict some disease and you'll be using the treatment that has been prescribed as a consequence of the diagnosis to predict the condition of the patient. So you can't diagnose, from data using information that was made available only after the diagnosis was made, namely the treatment. So I mentioned already that it's very important to have incentives in the challenge to make it useful. But another thing that's very important is for the organizers to reap themselves the rewards of the challenge. So what are the rewards of the challenge for the organizers? Well, it's harvesting the results of the challenge. So why did they put in so much effort in the first place if they're not interested in the results of the challenge? Well, I can tell you as the challenge organizer, sometimes by the end of the challenge we are completely drained. It cost us so much effort that we are not thinking anymore about doing the most important thing of all, which is harvesting the results. But you need to put this extra effort if you want to really have an impactful challenge. So you want to first have fact sheets that are going to be some kind of surveys, to have the participants describe their methods. You want to ask them to open source their code. So one way of doing that is to give the prizes only in exchange for the participants to open source their code. You want to eventually organize a workshop. You want to edit proceedings. You may want to co-author a paper with the winners. And last but not least, you might want to organize a follow-up challenge, because sometimes the first challenge is just only a warm-up, and then you can build a community over a year that gets better and better at solving your problem. There are, some problems that have been, some challenges that have been going on for years and years before there was a breakthrough that made a real advance. The example, for example, is the CASP challenge of protein folding prediction, in which there's been a breakthrough using deep learning recently. All right, with that, maybe in the meantime, some of you have already created an account on Codabench. If not, I'm showing again this slide. And you can get the instructions on how to get an account there. And this very brief tutorial will get you started to organize in a few clicks your own challenge. So Codabench is a platform that has, many of the desirable features of challenge platforms. Compared to other platforms, we like to think that it's full-featured. And it's been developed over many years, starting from a project at Microsoft. And some of the challenges that have been organized, big and small, include the societal, industrial, and ethical problems. Codabench allows you to either do a code or result submissions. So if the participants submit results, they are being then processed by a scoring program that's written by the organizers. And if they submit code, then the code is processed by an ingestion program that is run to create predictions that are then processed by a scoring program. And both programs are written by the organizers, so you have complete control over how you can run your challenge. So if you follow, this code, you get again to the getting started instructions that you possibly already got to. And this illustrates that Codabench allows you to organize your challenge by having a bundle. It's like the LaTeX of challenge organization. You have a configuration file, and you have all the files that are needed to organize your challenge, like HTML files describing your problem, and data files, and then the scoring program and the ingestion program. They're all bundled in a zip file that you can upload to the website, and then ta-da, your challenge is organized. So this is the page that you get to when you want to follow the tutorial. And what you need to do after creating an account is downloading the sample competition bundle and then the sample submission. Then you go to benchmark management, and then you get to upload your challenge bundle. And then, ta-da, your competition gets created from the files that were in the zip file. Then you need to, then if you want, you can, afterwards, you can still edit the challenge, or actually you can use the editor to create a challenge from scratch if you wanted to. But the real, ease of use of Codabench is to use these challenge bundles. Then to participate, you go to the Participate tab, and you can upload your sample submission. And then you can you can select to show it on the leaderboard, and then you can see, your results on the leaderboard. The leaderboard is configurable, and you can have multiple tasks or multiple data sets that show on the leaderboard. If you have a benchmark rather than a challenge, then it's a leaderboard that is ever growing, and then the same participant can submit many times, and you have many entries in the table that correspond to the same participant, whereas in a challenge, you only have the last or the best entry of each participant showing on the leaderboard, and then the duration is limited. But otherwise, it's very fairly similar. And then you have admin functions. So you can manage the participant list, monitor submissions, make hot changes during the challenge, and add compute workers. So what does it mean? It means that you can use the interface of Codabench and have the front end of Codabench hosted by the computers at Université Paris-Saclay do all the work for you of managing your challenge, and still have the submission run on your own computers. that can be hooked up to the backend of Codabench. And that allows us to run small and large competitions. If your competition is very computer intensive, then we ask you to provide your own compute workers. If it's, simple and just a class challenge with result submission, you can use the default compute worker and you don't have to provide your own compute workers. So in conclusion, Codabench is a versatile open source platform that we make available to everyone to create challenges. We have an upcoming open access book that gives you all the tools to organize challenges and get closer to frictionless reproducibility. We are hosting a free instance of Codabench that you can use. There are some current limitations that we are working on, and we are open to adding more features with the feedback of the community. Future enhancement, include having a competition template library where you can share competition bundles among organizers. But already now, if you are, recurrent challenge organizers, you can save your competition bundles from previous years, modify them a little bit, like change the data set, and dodom, you're ready for your new competition very simply. And before I close, there are a few advertising. My colleagues have been putting together a format for data sets that is very generic and will be facilitating both data-centric AI and challenge organization. There is a new journal, the Data-Centric Machine Learning Research Journal, for all people who want to submit papers in data-centric research. And there is an ongoing competition for AAAI for AAAI for education on math problem solving. And in bonus, as I promised, there is the test set formula that you can look up here. And finally, thank you for sharing the journey. And I hope that you will all become successful challenge organizers.
Okay, so the very end of the tutorial, where do we go from here? Well, first you saw that a lot of our tutorial was very much focused more on the practice side rather than on the theoretical challenges associated with data-centric AI. And we believe that really very bigger involvement is needed to really create the theoretical and potentially mathematical foundations of this data-centric AI agenda, thereby requiring a dual-pronged approach that looks at limitations and methodological barriers associated with the data-centric AI. We alluded quite a few times during the tutorial about the multimodal challenge, the fact that data-centric AI is not looking at just one modality or one type of data, but rather multimodal data. And I'm highlighting here tabular time series as graphical modalities as themselves posing significant challenges in addition to multimodality. Nabeel has talked quite a lot about this DC check, which is really a framework that we have put together to build new paradigms for training, testing, and deploying machine learning models. And clearly, on one hand, large language models can be empowered by the data-centric AI agenda because it is the quality of the data with which they have been trained that will lead to high-quality results, but also vice versa. Large language models can tremendously empower the data-centric agenda. And finally, data-centric is just one aspect of the puzzle. We really want to build high-quality, reality-centric AI that can be really useful for a variety of applications in the real world, going beyond just simple toy problems. So the takeaways are, let us aim as a community to engage with complex real-world problems and be aware that such a reality-centric AI agenda will require dealing with real-world data. Hence, data-centric AI represents an important aspect of this agenda. And for the people in the audience that are focusing on synthetic data, let us try to look at synthetic data not only to replace real-world data with privacy-preserving data, but also improve really the ability to engage with a variety of issues, from fairness to augmentation to better testing our models. So this requires us to retrain, to rethink how we do training, testing, and benchmarking from a data-centric perspective. We are not operating in isolation. Increasingly at all our main conferences, we see data-centric machine learning research ecosystem emerging. And in this recent paper by Luis Walla, this ecosystem is described. So we hope that you, after following this tutorial, will become part of this ecosystem and contributors to this ecosystem. Our slides can be found again at this QR code where you can download them. And what we are going to do next is take a few questions, and finally we will have our panel discussion. So while our panelists are getting ready, it is time for a few questions, and maybe, I don't know, Isabelle and Nabeel, maybe you two can come here as well, since the questions may be for all our tutorial.
Hi, thanks for the interesting talk. Many of the problems that you've identified in data-centric AI seems to me that they've long been appreciated in the statistical communities and scientific communities. Do you think we have veered far enough from these fundamentals that we're now coming full circle in trying to redress them? So, for example, you talked about generating synthetic data with generative causal graphs. If I have a generative causal graph, why do I need to generate synthetic data to then feed to an agnostic model downstream?
So I guess this question is addressed to me. So two parts, two parts to the question. So first, it is clear that in the data-centric AI, the machine learning community can tremendously benefit by joining forces with other communities, in particular the statistics community. So that is definitely the case. And I would say, conversely, if we can solve these data-centric aspects of dealing with both data as well as training, not only the machine learning community can be empowered, but also the statistics, econometrics, and many other communities can really benefit. So on one hand, we hope that they join forces with us to address these challenges, but also conversely, I think if we address these challenges through machine learning, they could benefit. With respect to the question on using a causal graph to generate fair synthetic data, again, the purpose here is not to build a machine learning model necessarily. The focus here is to generate fair synthetic data that could be given, for instance, to run competitions by different types of machine learning models. So let us not forget that at times we are just focusing too much maybe on just the models, and the models may be numerous. So trying really to create high quality fair synthetic data could represent a first step, and then the challenge comes of really identifying the best machine learning model for this data. So that's one of the many examples where the two steps are separated. First data generation, followed by model training.
Thank you.
Hi, I'm Gerald Farner. My background is credit risk scoring, and thank you for your insightful presentations. I have a question regarding the use of synthetic data for testing models or stress testing models when distributions change or on underrepresented subpopulations. And so my worry is that the synthetic data model itself may be erroneous, and if you use it to generate synthetic data on subpopulations that are not well represented in the training data, then wouldn't that compound the problem? And in addition, if the generative model is a black box, I wouldn't even be able to diagnose it.
No, thanks so much for the question. So I think it is a definitely 100% very valid concern. So I think one thing that maybe we didn't fully cover in this bit of the tutorial was, so in the case where you don't have as many samples, or in a distribution shift setting where you obviously have to make some assumptions first of what prior knowledge you have. One way we've tried to address this, and this is definitely a first step and much more should be done, is building on from the ensembling community of actually building an ensemble of generative models. And then actually when you generate the synthetic data, having intervals over what you generate. So you have some degree of uncertainty that a sample of how realistic you think it is based on having this type of interval. And then on the basis of the interval, a practitioner should decide how much they should trust the synthetic data or not. And we're able to show, of course, like when you have very wide intervals, the synthetic data is going to perform badly. And when the interval is actually pretty good, you can more realistically trust the output. So I think much more should be done on that direction with like the ensembling approach, just one approach, but definitely much more can happen there.
And if I can jump in on that, on the fact that black box models, don't forget that in this case, you are generating synthetic data and hence you generate data. So ideally, and I think you are alluding to this, ideally you want to have a human that's knowledgeable about this domain, that is going to inject this know-how and this prior knowledge in this generation. This could be done either as a prior to guide the generation or as a validator. Otherwise, like you say, you may generate a lot of crazy examples on the basis of which you select models, and that makes no sense.
Oh, thank you. Can I ask you something directly to that? What do you think of using Bayesian networks for synthetic data generation instead of variational autoencoder kind of black box architecture?
I love it.
Okay, thank you.
Thank you for the great tutorial. It's very low. I'm very tall. So when you generate data to build better pre-trained models to then later on do new applications for, do you take into consideration what the new application is? So say if the new application is maybe our distribution, would you generate data more towards the distribution, or would you generate data more generally to allow better transfer to that new task?
Well, so this a little bit relates to the previous question. So I think that knowing something about the use scenarios where we are going to deploy this model will help in the generation. At the same time, one could take into consideration lessons learned either from other deployments or from, if we talk about competitions, other competitions, and use that type of knowledge to generate this new synthetic data. So the more knowledge you have about these scenarios, the better. On the other hand, one could say, well, let us try to generate as many realistic settings as we can, such that when we are taking this model to the real world, it will see missingness, it will see noise, it will see errors, and will still be able to really work robustly. So what I really hope is, as Nabeel said, this is the beginning of the journey, and we really hope to entice the machine learning community to think much more systematically and come up with innovative ways of rethinking the use of synthetic data to better test our machine learning models. So create a simulation environment like the wind tunnels of the aviation industry to stress test machine learning before we put it into the wild.
Wonderful, thank you.
So I also have a question like related to generating synthetic data. So like after you do the data augmentation or generating lots of synthetic samples, one important thing to do is to do data selection based on the quality of the synthetic samples. For example, when you do the semi-supervised learning, you generate pseudo labels on the unlabeled data, right? But how can we select the reliable pseudo labels is a very important thing. So I'm wondering what are the main principles for like measuring the quality of the synthetic data?
So I guess there's maybe two bits of the question that I can probably answer. So the first is probably related to, you mentioned like semi-supervised learning, pseudo-labeling. So I think a lot in the first bit of the tutorial where it talked about this idea of data characterization, where that you do ultimately have a label that you're assigning. So some of those methods are actually are very much applicable in that case there to assess the pseudo label, because basically if you're assigning an incorrect or bad pseudo label, that similarly amounts to something like mislabeling on like a supervised data set. So in terms of auditing there, that is definitely one interesting angle. And then I guess on the synthetic data side, I'll allow Mihaela to talk a bit more there in terms of like the synthetic data metrics for doing actual evaluation when you generate actual samples themselves.
So I'd like to introduce our esteemed panelists, Dr. Jennifer Wolfman from Microsoft, Professor Guyon Cho from NYU and Genentech, Dr. Jim Wetherell from AstraZeneca, and Dr. Răzvan Pașcanu from Google DeepMind. So thank you very much for being with us online. We have a first question to all of you, and that is, what is the most exciting aspect of the data-centric AI from your perspective, and why do you believe that the machine learning community or beyond should pay attention to this research agenda on data-centric AI? And we are interested in hearing your personal perspective on the unique opportunities and transformation that data-centric AI brings to your unique field in data science in general and machine learning in particular. So maybe, Răzvan, I start with you since I see you.
Oh, okay.
You are the one that is featured online, so maybe I start with you.
Okay, perfect. First, thank you for having me. Let me see what I can say. So first of all, I'm not fully a data-centric person, I would say, so I'm still living between things. But like one thing that I find quite important is that you can't avoid looking at the data. I mean, I think this is something that became visible more and more in the last few years. And so it's definitely true that the quality of whatever you do depends a lot on the data, and that's why the community should care about. The reason I care about personally is because initially when I was thinking about this aspect of the problem, I thought it's more about curating data and making clean data, but I think it's a lot more than that. So just to give you an example, recently with some folks from ETH, we were looking at compositional generalization. And it turns out that if you want a system to kind of have this kind of behavior, to be able to generalize in a compositional way, there's constraints on the data that you learn on. I was just saying that there is a lot more to data-centric perspective than just curating the data, right? So there's like fundamental properties that you want to get from a system. You can't get them unless you have the right data. And there's a science to it, and that's sort of what makes it exciting for me. So it opens the door to a lot of interesting research questions about what is the right data to learn a particular kind of behavior. It opens the door of better evaluating systems. Like I think the typical way of evaluating systems is broken at the moment, and like just because we can't control test train contamination anymore. So this all open a lot of interesting questions that need to be figured out, and they're all just focusing on the data. Sorry, I feel like I'm talking too much. I hope that made sense.
Thank you, Răzvan. Jen, what is your thought about this?
I'm Jen Wortman-Vaughn. I'm a researcher, but I work in responsible AI in industry. So that's the perspective that I bring to this discussion. And in industry, building AI systems often requires taking this data-centric view. This is not a new thing. This is how it's been for quite some time. And likewise, addressing responsible AI in industry settings often really requires this data-centric view as well. The first time that I personally really appreciated this myself was back in 2018, so about 6 years ago now. I just started shifting my research into the responsible AI space, and my colleagues and I at Microsoft Research were reading all of these papers that were proposing ways of making machine learning models more fair. And this all sounded fantastic, so we got really excited. We started reaching out to product teams within Microsoft to chat with them about some of these ideas and find out what would be useful to them. And it just became apparent to us very quickly that the predominant way of thinking in the literature was just not a match for the problems that product teams really faced. This is something that we talk about in a CHI 2019 paper. But basically, one of the biggest issues that we were seeing was that proposed solutions in the research literature tended to be very model-centric. And as Nabeel said during the tutorial, the research community often thinks of training data as just fixed and really focuses so much on model iteration. But when addressing fairness issues, product teams didn't want to make huge changes to their models. This was just something that was not feasible for them. It was a non-starter. When they encountered issues with fairness, the first question was, how do we collect more data? Or how do we collect different data? Or how do we collect better data that will help us address this? And these are the types of questions that they really wish that researchers would be focusing on more. It really struck me because these are just such obvious questions in retrospect, but at the time, that's not the way that anyone was looking at things in the responsible AI community. One other thing I'll briefly mention is, back around the same time, 2018, my MSR colleagues and I started working on our proposal for dataset documentation, which is what grew into data sheets for datasets. And we thought this was really critical because, done well, data sheets can help dataset creators reflect on the process that they use to create a dataset, reflect on underlying assumptions they're making, potential risks and harms, implication of use, and so on. It can help dataset consumers ensure that they have the information they need to make informed decisions about whether and how to use a dataset, and so on. I know that you asked for exciting aspects of data-centric AI, and not everyone out there finds data documentation quite as exciting as I do. But I think that getting documentation right is actually really critical. And honestly, we're just not there yet in terms of how widespread data documentation is, or in terms of the quality of it. Mihaela, you mentioned this quote earlier about how data work is undervalued and deglamorized, and I think that is even more true for dataset documentation, and we need to do something about that and figure out how to kind of get the incentives right for people to take this seriously. Because not taking this seriously, rushing through, doing it in an ad hoc manner can really lead to huge problems down the line when data sets are used in inappropriate ways.
Guyon, maybe I'm going to you next.
Yep, sounds good. I'm at both Razvan and Jen just gave the amazing examples. So I'm going to step a bit further, and then hopefully I'm not going to actually say exactly what Jim was planning to say. I'll try my best. So as we increasingly deploy more machine learning systems in a more diverse set of, let's say, scenarios, what we are seeing is that in fact, our basic assumption that the past reflects the future is breaking down. And in particular, in discovery setup, for instance, drug discovery or the scientific discovery, where we are trying to use all those recent advances in large-scale language models as well as the generative models for finding something that we never actually found before. And sometimes some things that nature has never found before. What we are seeing is that by definition, data has to be scarce. That is, no one has collected the data for us to simply use whatever the algorithms that have been published in NeurIPS or whatnot. And then what that means is that we are always in a scenario where we have to produce more data and collect more data. Then the question is, what is the right way for us to collect such data? And then that's where I think the data-centric machine learning comes in, is that the data has to be collected with the purposes. So a lot of times we kind of say, I believe that they're fooling ourselves by saying that with self-supervised learning or the amazing unsupervised learning algorithms, all we need to do is just use all the data that has been collected by the humanity and have been stored in the internet without necessarily a single purpose that we wanted to use, and then just pour them in, and then it's going to just give us the amazing representation that allows us to do the discovery. And I believe that is the way in which we fooled ourselves. In reality, what we really need is to think about what are the new things that we need to discover in order to benefit the humanity. And then in doing so, we have to start thinking about not only the model, but also the whole framework under which we can collect the data, either by running the experiments or actually going into the out there to collect them. And then the data has to be collected with purpose. So how I see the data-centric machine learning from the perspective of the discovery is to collect data with the purposes, and the purposes have to be known in advance for us to maximally use and benefit from data.
Thank you. Jim? You are the last.
Thank you, Mihaela. for giving me both the privilege and the great challenge of going last and trying to say something intelligent when the three previous speakers have done such a great job. But I think, generally, this is a movement that I'm very much in favor of for some of the reasons the previous speakers gave, so I won't repeat that. But I think for me, the exciting bit is getting researchers and engineers to kind of shift the mindset towards data, which I think is a difficult journey because of the model focus we've been on to this point. So that's a general reflection. But I think what you really want to hear is specifically what this means in our domains. And so I work in biomedical research, of course, trying to develop new medicines for humanity and for the good of the world, which Guyon just mentioned. And I was asked recently how to respond to the observation that the first group of AI-driven drug discovery new companies, the medicines they discovered were failing in clinical trials. And why was this? Because this was supposed to be the great antidote. All the data was there. You just had to have some smart AI and some smart engineering, and this would find the medicines of the future. And I thought quite hard about this, and I don't want to digress too much, but one of the reasons I came up with, and we can debate this, but I don't actually think there's as much data out there as we think there is. Biology's really hard and almost infinitely complex. And so when we say there's a lot of data to solve this problem, we just need to model it, a lot of data relative to what? And I think even in the most simple biological system, for instance, how just a single cell works is incredibly poorly understood today. So I think taking assumptions from other sectors and applying it in the one in which I work with the assumption that there's a lot of data for the problem in hand is probably misplaced. And that only really dawned on me relatively recently, and I've been working in this field for sort of 20 years. So I thought to pick up on some of the previous points, absolutely, if data-centric AI can help prompt us as to the data we do need to collect and the kind of questions we can ask and get meaningful results, I think that's going to help everybody, because then we're not going to have failures when we try and bring new medicines to patients. Of course, in research and development, there's always some successes and some failures, but we're really trying to move the needle here. And to me, the competitive advantage, so I get asked this question a lot, right? Because I work in a business. What's the competitive advantage? And I increasingly say to people, it's becoming less and less about the actual modeling approach, because sooner or later, people figure out how to model stuff, everybody catches up. The uniqueness is the data you're generating your scientific experiments. That gives you a chance of competitive advantage. So that's the other way to think about it. The special sauce is becoming the data. AI is becoming democratized.
Thank you so much, Jim. Okay, I'm now moving to some specific questions to each one of you. And the first question is for you, Guyon. In what ways can a data-centric AI approach enhance the reliability and efficiency of large language models? And additionally, how can large language models, given their significant prior knowledge, further empower the data-centric AI initiative? So I'll ask you to put your NLP LLM hat to answer these questions.
Oh, that's a really difficult question. So perhaps I can say something like, probably not how we can actually use the data-centric AI or the machine learning in order to improve the large-scale language models, but some of the concerns I have in training these large-scale language models. So before I begin to answer this one, I want to say to everyone, there must be quite a lot of people there, we can't really see the audience, that we can always train these large-scale language models from scratch if we have the will and then the investment that we can find. And then all these companies, in particular if there are companies, and then if you feel like so, and then if you feel that it's important, you shouldn't rely on a single vendor or the single company to build a system for you, but you have to actually build these large-scale language models yourself. And I'm doing that at Genentech and Roche, so if you're interested in this, I'm going to be at New Orleans in about, let's say, 5 days, so come talk to me. So that aside, while training this kind of large-scale language models, what worries me most is the lack of transparency. What do I mean by the lack of transparency? It's not about the, let's say, model itself, because you go into Hugging Face transformers, you go into, let's say, Mistral's code base, you go into, let's say, Lightning and Lightning GPT, you find all the codes that is available that for you to actually use immediately and start training the model. That's fine. And I'm not actually worried too much about the availability of the compute either. So if it is really important and there is a business case, you will have to figure out how to get the compute. Compute is out there, just that often they're expensive and it's difficult to justify the business use cases. But what is really difficult for me to understand what is going on behind is what's inside data, and then how the data was collected, and then what were those purposes that people actually had initially to produce those data that have been aggregated. So we do use all those data that is on the internet. So people would simply say that, well, they're all publicly there, so why not just use them? But publicly available does not necessarily equate to I know exactly how they were produced and what kind of content is this and there is, and then what kind of consequences we're going to get by training these models on those big data. So what, to me, data-centric ML is really important, especially in this kind of large-scale language models where the transparency is increasingly not there anymore, is because it really forces us to think about the data that we use. I don't know if you noticed, so yesterday and day before, and then we actually saw it within Genentech a couple of weeks ago as well, is that we trained our model from scratch ourselves in our data mixed up with some of the public data. And then we fine-tune it with some of those conversational, let's say, supervised data that is available online. And then we did a very meticulous, let's say, filtering. Thereby, we don't actually have any of the data that says as an AI language model, which is a kind of emblematic, let's say, sign that response was generated by OpenAI's models. We removed them really in the fine-tuning data. And somehow our model was still responding to our questions by saying that as an AI language model, which is weird, but that is not really weird because the pre-training data we use was already rampant with all these AI, GPT-generated data sources. Now, what that tells me is that I'm very worried about this whole, let's say, notion that, okay, modeling is really important. We just make a better model and then use whatever the data that is out there, we're going to get there. Because at some point, our models are not going to learn from the collective information that humanity has created up until last year, but rather we're going to simply train a model to learn to repeat what Sam Altman wants us to listen to. And that's actually something that worries me most. And then when it comes to reliability, we have to know what the data is in order for us to even talk about what it means for our models to be reliable.
Thank you.
So not an answer, but yes.
Thank you. Well, this is a perfect time to move to the next question, which I think is somewhat related. And this question is for you, Jen. What further advancements are needed within the realm of data-centric AI to better facilitate and ensure responsible AI? And how can data-centric AI be more effectively leveraged or evolved to address ethical considerations, fairness, and bias in AI systems in general?
Yeah, that's a great question. I think that there are actually a lot of advancements we need here, but just to name one that I care about a lot, I would like to see more effort placed on collection and labeling of high quality evaluation data sets. This idea of collection with purpose that was brought up earlier in the panel. And there are reasons that we don't see as much of this as we should right now. Collecting high quality data is super expensive in some cases, and it's just really hard to do. And again, this is undervalued work in general. But it's so important, So one of the ideas that I've worked on a fair amount is how to design and execute disaggregated evaluations of AI systems. So these are evaluations where system performance is assessed and reported separately for different groups of people, usually broken down by demographic group. And, there are actually a lot of, this sounds like such a simple idea. Everybody thinks this is very trivial to do, but it turns out that doing this in practice is incredibly hard. And in a study my colleagues and I ran looking at industry practitioners' challenges in conducting disaggregated evaluations of the products that they were building, we found that data set collection was actually one of the huge hurdles here. So practitioners talked about tensions between their organization's privacy requirements and the need to collect demographic data. They mentioned a lack of expertise in how to properly collect demographic data, which needs to be done very carefully in different ways in different contexts. They mentioned the challenge of collecting evaluation data from sufficiently diverse populations and how, as a result of this, often they ended up focusing the most on populations that were easiest to collect data from and prioritizing those, which actually exacerbates fairness issues, and so on. And these are problems that I see coming up in industry, but I would really like to see the research community paying more attention to the data sets that they use for evaluation as well. And I think this is getting especially critical at this point in time that we're at, when the line between research and deployment is becoming so blurred, and techniques that are developed by researchers are actually ending up implemented in real products and services very quickly. So, given all of this, we should all be questioning things like, when we have an evaluation data set, where do the labels actually come from? Are these labels actually valid proxies for what it is that you care about? Are the populations that you care about represented in the data? Does the data match the real world conditions where a system might be used? And so on. Again, especially when there's a chance that the system is going to be deployed and impact real people. And I just want to emphasize that these are not always problems where automation is necessarily going to help us. And I know that this makes some people extremely uncomfortable, especially, at a venue like NeurIPS. Automation can be very useful to pick out some kinds of issues, but if you really care about the data-centric perspective and you're committed to building AI systems responsibly, there are some scenarios where we just really need to be willing to slow down and include a human perspective as well. Again, this is one of the ideas that we really emphasized in the data sheets work as well. Automation has value, but we can never fully get rid of this need to think carefully about what we're doing and whether it actually makes sense. I'm talking generally about machine learning here, but I think the same problems are coming up in this new age with LLMs and generative AI. Evaluation there is super important as well, and it is quite a mess right now. And I would just like to see a lot more attention paid to good evaluation data.
Thank you, Jen. Could not agree with you more. I completely agree. So, Jim, now coming to you. When thinking of data selection and acquisition methods in data-centric AI, and you already spoke very eloquently about this earlier, what role do you think this will play in clinical trials and other more challenging areas in the pharmaceutical industry? And related to that question, how would regulatory aspects play a role in driving this data-centric AI?
Yeah, thanks, Mihaela. It's almost like I've set up my second answer by laying the platform with my first. So yeah, if I sort of continue maybe what I was saying before about the amount of data we actually have to play with in biomedical science for any given question, and that it may be less than we think. I do think, on a positive note, if we can get data-centric AI right, we'll develop methods and approaches and processes that tell us things like, based on the data we've got, what data do we need to collect next? Which experiment do we need to run next? Based on the objective, the disease we're trying to treat, the patient population we're trying to help, where are we weakest? Therefore, where do we need to double down, collect more data, or possibly impute or create synthetic data? So there could be lots of different roles for data centricity to play in this space. And if you think about it, and this is kind of my dream in a way, that would be an incredible way of doing clinical research, because you would be collecting just the data you need to answer the medical need that you have, and it would be very targeted and hopefully done in a sort of minimized ethical way, also in a sort of responsible way. Clinical trials can be very expensive. They can expose many patients to an experimental medicine. And again, you want to do that in as focused a way as possible. So if the methods out there can help us to make the decision about what's the next experiment to run, get those medicines to patients as soon as we can, I think that's really the goal. I think the complication that was or the additional challenge in the second half of the question is that we are a heavily regulated industry, of course, particularly when medicines are being trialed in human beings, quite rightly. And I think there's a huge importance there of bringing the regulators and other stakeholders along on the journey. So, for example, if we were to implement techniques and methods that made automated or even semi-automated decisions about which data to generate, which patients to select and recruit into our clinical trials, how to triage that data, how to analyze it to come to conclusions about the efficacy and safety of those medicines, then it's quite a journey to change the regulations so that we've moved the goalposts on how new medicines can get approved to go onto the market and be available to patients. So I think the short answer to that part of the question is it has to be a big conversation. It has to be transparent. It should involve people in general, and particularly the patients who may end up becoming part of these research trials. And certainly it should involve the companies, the academic investigators that work on these trials, and as we said, regulators, who are the ones who are really the custodians of the rules of the game here as to how new medicines get approved. So data centricity could transform this field if we get it right, but you've got to bring everybody along on the journey.
Thank you, Jim. So Razvan, regarding the future synergy between model-centric and data-centric AI paradigms, what fundamental developments in machine learning do you believe are necessary to facilitate this integration? And if we are successful in doing so, can this type of synergy propel further cutting-edge machine learning research, and how?
Yeah, it's a great question. Let me see if I can give it justice. So I think there is a huge interplay between the data and learning process itself. And I think there's definitely going to be a lot of development if we look at this more carefully. Particularly, I've been looking a lot at continual learning, which is learning under distributional drifts. And so far, the field itself, as usual, kind of focuses a lot on the model and maybe some kind of regularization terms that you need to throw in. But the question that is not asked as much is, what kind of distributional drifts do you want to deal with? And then it turns out that you can't have some kind of magical solution, some kind of regularization that would work for any kind of change in your data distribution, right? So the ability, there's a lot of trade-offs that you need to do when you learn, and these trade-offs depend on the data that you're seeing and what your ultimate goal is, right? So there's all this talk about forgetting versus sort of the ability to learn faster. It doesn't seem like you can fix all of them. Like, you need to do trade-offs, and those trade-offs depend on how much the data, how much distributional drift are you going to have, and what exactly do you care about. So I think the synergy comes here by basically understanding how these things relate, like how the learning process works, and how, I've been also saying quite a bit that there is, if you look and you have all of these metrics that tells you that you have data points that you learn and then you forget and you learn them again. There is something about the order in which you see the data. So think active learning or in this that has to. If you see the data in the right order, you can get orders of magnitude efficiency in how you learn. You could potentially not need to go through these cycles of always learning something, then forgetting, and so forth. So I think if people would take sort of the data into account a bit more and think a lot more about sort of the relationship between data points, think a little bit more about sort of what distributional drifts are, this could have a huge impact when you on the learning process itself and on the model as well. There's also an interplay that we tend to ignore between the expressivity of the model, what the model can represent, and sort of what the data requires to represent. These things become quite interesting, particularly now when you have these LLMs. People like to use these LLMs to do all kinds of algorithmic reasoning stuff, for example, a simple thing is math. But we rarely stop and think okay, can we actually represent sort of the algorithm of multiplying two numbers within the transformer computation? What does it take to do that? And what data should I see in order for me to understand the algorithm from the samples? And I think from a theoretical point of view, there's a lot of things that we can find if we start asking these questions the right way. Not sure if that makes sense, but yeah.
It did. Thank you so much. Thank you very much again, Jen, Jim, Guyon, and Razvan. Thank you very, very much. And thank you especially to Jim, who stayed very late to be part of this. So thank you all very, very much for being with us.